Hey everybody. So as you may be able to guess by now, I am a undergraduate math major. Um, and one of the things that we just did in my calculus class is Fourier series. So I kind of just wanted to make a video to explain a little bit about them and show off how cool they are. So if you've got a knowledge of, say, like Calc 2, Calc 3, you'll be able to follow along everything in this video. But even if not, you are going to see some pretty graphs by the end. So stick around. But before we talk about Fourier series, we have to talk about periodic functions. So what the heck is a periodic function? The two most classic examples of periodic function are, of course, sine and cosine. These are just waves. Everybody knows them, everybody loves them, and the reason why they're periodic is because they repeat over and over. If you take your cursor and you drag along the function like this, you'll essentially get to a part of the graph that looks the exact same as what you just did. Just like that. And if you go out all the way to the right, you'll see that they repeat over and over again. There's nothing special going on, they just repeat. And so there's a couple things that we can do with these functions. We can shift them. We can shift them up like that. We can shift them down. We can shift them to the left and to the right, although it's going to be a little hard to see. That's me shifting to the right, and that's me shifting to the left. But that's a little hard to see. We can stretch them. We can stretch them up and down like that, and then we can stretch them, side to side as well, and that's going to look like that. It's going to look like that, yeah. And it turns out the one that's most relevant for us is when we stretch them side to side. So when we've stretched them like that, what used to be, let me have this as well. So the purple one is just what we had before. What used to be, a period of 2 pi, right? This is 2 pi. That was our period. Now for the green function, it's going to be twice that. So here, this is our period for the green function. It's 4 pi. So now we've stretched the period out twice as much. And yeah, that's relevant because we're able to play with these and we're able to do what we want. And the reason why these functions are periodic is because of this relation. Take any value of f of x that you want, go along the function a period of t, whatever period your function has. Here, the purple function and the blue function both have a period of 2 pi. The green function has a period of 4 pi. These periods are determined by the function, but whatever period your function has, go over that much, and then the value of your function is going to be the same. And that's for wherever you start. You could start, at where your period starts. You could start in the middle, and go over like that. You could do whatever you want. And this is going to be relevant later, but this idea of a periodic function where all you have is this relationship, this is actually a class of functions that's much bigger than just you've got sine and cosine and whatever you want to do to them. No, here sine and cosine, they're nice continuous waves and they're smooth, they're infinitely differentiable, but a periodic function doesn't have to be. It doesn't have to be continuous. It doesn't have to be smooth. It doesn't have to be differentiable. It doesn't have to be any of these things. So what does that kind of look like? Here's an example of that. Let's take the graph y equals x. This is the most simple graph. It's a straight diagonal line. This is not a periodic graph because you can see it just goes up, 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 and it never really repeats. But something that we can do is we can take a pair of scissors and we'll snip the graph at x equals 0, and we'll go along the graph and we'll snip the graph again at x equals 1. And once we have that little bit of the graph, we can copy paste that onto 1 to 2, 2 to 3, 3 to 4, and over again. And what that looks like is it's going to look like this. So here the purple function is exactly what I said of that portion of the graph that we snipped out, just repeated over and over again. And here, this is a differentiable function, but it's not continuous. It's not continuous. And it's also not differentiable at each of the whole numbers, each of the points where it crosses over. It's not differentiable at those points, but it is differentiable at every other point, essentially. But yeah, this is an example of a periodic function that's not continuous. But, you know, I said that we were snipping the graph at 0, we were snipping the graph at 1, but why? Why does it have to be 0 and 1? The answer is it doesn't. What we can do is we can change where we snip the graph, like this. So this is me changing where we snip the graph, the bottom point, and then this is me changing how much of the graph we snip, so essentially the top point. And we're able to kind of do this. So yeah, we, just like we had all of those ways that we were able to do, like up at the top, we were able to shift it left and right, we were able to stretch it up and down. We're going to be able to do all the same stuff here. So here, if I want, I can shift it up like that. I can shift it to the right or to the left by changing the period. I can stretch it by changing the period. I can do that. I can do all sorts of things. And we really do have a wide range of freedom as far as stuff that we can do. But one more thing that we can do is, so I snipped this graph at 0, 1, and I've already shown how it doesn't have to be 0, 1. But this is the graph y equals x. It's probably the most simple graph of all time. Why does it have to be this simple graph? The answer is it doesn't. Let's take the graph y equals x squared. This is the parabola that we all know and love. But same idea. I want to snip the graph at x equals 0, and then run along my finger along the graph, snip the graph again at x equals 1. And so here, instead of a straight line, we've got a little bit of a curve. But what if I want to repeat that curve over and over again? What that looks like is, so I'm going to take this expression, and I'm going to put it into this function everywhere I see an x. So what that's going to look like is just that squared. And there we go. We've got this graph, this curve that we're repeating over and over again. And we can do all the same stuff that we did before. We can shift it, and you can see it follows the course of the graph like that. So let's kind of zoom out to see what's happening. Just like that. That's pretty sick. We can also change how much of the graph we snip. So there we go. That's pretty cool. I think that's pretty cool. And you know, we can also have other graphs. One of my favorite graphs is x times sine of 1 over x squared. I call it the bow tie function because it looks like a bow tie. And how this is going to look like is same thing. We're going to take this expression, put it into here, and so what that looks like is that times sine of 1 over that squared. And yeah, we're just gonna go along with it. So there we go. And we can play with it. We can do all sorts of things. We can even put a 2 out here and make it tall. But enough of that. Yeah, so that is a way to make any function periodic. Any function you want. I should say any elementary function. I'd imagine it works with special functions as well, but I haven't tried them. But as definitely any elementary function, any function involving powers, roots, logarithms, e to the x, sine, cosine, all these things. You just take this expression right here. You're able to control your a and your t, and then you put it into the function that you want to make periodic. So that's all on periodic functions. Let's start to talk a little bit about Fourier series. But before we do, we have to get into a couple things. We have to get into what's called characteristic functions, which are these guys. And here, this capital X, it's really the Greek letter chi for characteristic, but sadly Desmos does not have a chi letter, so I'm using capital X. It's denoted as e to the 2 pi I in x, where I is the square root of -1. Desmos is asking me to add a numerical value for I, but I is the square root of -1 here. So it's a complex thing, and because it's a complex thing, I can't just plot it into Desmos. But what this function really looks like is imagine the unit circle in the complex plane. And imagine a particle moving along that circle, and it's moving at a certain speed, and the speed we are able to vary because we have this n here that we're able to change. N is a parameter, but it's moving at a certain speed. For higher values of n, it's going to move at faster speeds. For lower values of n, it's going to move at slower speeds. And then whenever we do complex numbers, we have to talk about taking the conjugate. And taking the conjugate basically means you're going to flip it across the x-axis or flip it upside down. And what that essentially does is make the power negative. And that's how you take the conjugate. It's really, really simple. When you take the conjugate, you're just going to go around the other way. And that's it. So that's the characteristic function, e to the 2 pi I in x. And once you have that, you take your conjugate, you put it right here. You take your f of x, which was your Riemann integrable periodic function up here. I forgot to mention that the only two criterion for having a Fourier series is that you're periodic and you're Riemann integrable. And that's it. That's really it. That's why we're able to do all this magic. So you take those two functions, you integrate that from 0 to 1, and here the integral doesn't mean like taking the area under the curve, because this is a complex thing. So what does that even mean when you're talking about complex numbers? So it's a little bit different in how you need to think of it, but the kind of in practice it's the same. You find an antiderivative, you put in 0 to 1, and you get a numerical value that's based on your n. That's why this is a function of n here, because we integrated out all the x's, but we're left with this n right here. And this is the Fourier transform. This is the Fourier transform of your f of x, is in your n space, essentially. And because of the nature of this integral, you're going to be doing integration by parts a lot of the times, which is why this is a little bit hard. But yeah, that's your Fourier transform. And once you have your Fourier transform, you put your Fourier transform right here. this is going to be as a function of n, but then you're going to sum from n equals negative infinity to infinity times your characteristic function again. So here we took chi conjugate for the integral. For the sum, it's just going to be regular chi. And this is going to be a function of x, actually, because when you have all these functions of n and you sum them, you're just going to get a number. But for each number, what we call the Fourier coefficients, times that by a varying frequency characteristic function, you're going to get a function of x, which is pretty cool, I think. And big elephant in the room is this guy. How on earth do you sum from negative infinity to infinity? When I first saw this, I was kind of confused, but all this really means is you take your n equal to 0 term, you don't forget that, but then you also take your sum from 1 to infinity, and then you also have your sum from negative 1 to negative infinity. And that's really all that means. This is shorthand for this. Yeah, that's really all it is. So that's how to do that sum. And what's crazy about this is that whenever you do this series, even though this f hat is complex valued, even though this chi, for each n, it's complex valued, whenever you do the whole sum, it's going to turn out to be real valued. And I thought that was crazy, because you have the 0th term that you put in front, and here you can see if you put in n equals 0, you'll just get 1 here, because e to the 0 is 1. And so this is going to be 1, and so it's just going to turn out to be the integral from of f of x from 0 to 1. Here, f of x is a real valued function, so when you do the integral of a real valued function, you get a real number. And then this, of course, is going to be 1 again, and then it's just going to be the integral from 0 to 1. That's a real number. So here, this n equal to 0 term is a real number. But the magic happens right here. If you take the negative kth term and the kth term, for every single k, all the imaginary parts cancel out, and you get a real number. Or, sorry, not a real number, a real function, real valued function of x. And that's crazy. That's wild. If you can imagine, you've got this sum from negative infinity to infinity. You take the 0th term, which is kind of like right here, and then you're adding 1 and negative 1, 2 and negative 2, 3 and negative 3. So yeah, imagine this left line kind of wrapping around and folding on top of this right line. And then when you add all the terms in this right line, you get a real valued function. So that's really the magic of what's going on here, is that whenever you do this, you get a real valued function. But, of course, it has its drawbacks, and here the drawback is this is more oftentimes than not a freaking pain to calculate. Like, it's really bad, but what we know is that it's possible. And so if it's possible and you have enough dedication, you can do it. And what's an example of something that looks like this? So here's an example, is we've got this function, this red function, and here, this can also be called the characteristic function. Here, maybe it's called the identity function or something like that. But it's really not that complicated. All that we have is we've got this interval on x, a to b, and here we can control what a and b are. And our function essentially says if our x is inside that interval, then the value is 1. That's up here. X is inside a to b. If x is outside a to b, so down here and down here, the value is 0. And so this is a obviously it's Riemann integrable, but it's discontinuous, and it's not periodic because it doesn't repeat over and over again. But I want you to imagine in your head it repeating over and over again, kind of like where my cursor is going. The only reason I wasn't able to get it to repeat over and over again is just a limitation of Desmos. I probably could, in all honesty, it's just a little bit hard to do. So imagine this shape repeating over and over again, and what the Fourier series for that looks like is it's going to look like this. It's going to look like a bunch of waves put together that kind of approximate the red line. And so, yeah, you can see it approximating. And what's cool is that we can change what our interval is, and the Fourier series will adjust accordingly. I think that's so sick. I think that is so sick. And if we want to make it the whole line, then it just becomes the whole line. Something else that we can look at is here the waves, they don't really do a good job of approximating, the red line. Like here, like the waves are pretty big, but we can actually refine it. We can refine it like that. And with just, here I went up about 80 ticks. With 80 ticks, it's doing a much better job of approximating that. And then it shoots up here, but it's not discontinuous. It's continuous at every turn, at every in one. But it's doing a pretty good job. And then if we want, we can take it to 100, and this is the best job that we have. Now, obviously, if we go back up here, this it goes all the way up to infinity. Now, we can't go up to infinity because we're on a graphing calculator. But you can imagine if we were able to go up to infinity, then it would what we call uniformly converge to the red line, which is just a fancy way of saying it would become the red line at infinity, which is sick. That's really sick. And the expression for that is this monster thing right here. And this is an example of what I said earlier, where this is really kind of the hardest part of all this. Yeah, so that's what this kind of looks like. You can change, A and B and adjust accordingly. It's pretty cool. So whenever I was playing around with this earlier, I came up with a few more examples of stuff that we're doing. This is an example, kind of got like triangles, and this is a really good example of here you can see the shape of it. Like Fourier series always have a particular shape that I really like. It's like a weird like thin wire almost. You can see it'll overshoot like that, and then it'll kind of adjust. And this overshooting is what we call the Gibbs phenomenon. It's just really a fancy name for it overshooting. So this is what this one looks like. This one is what this one looks like. These are just me playing around with them. And then this one I think is pretty cool. That one's pretty cool. So yeah, that's a little bit about Fourier series. Sorry I haven't posted in a while. School has been absolutely crazy. What we're doing right now in calculus is the Riemann-Stieltjes integral, which is freaking wild. Maybe I'll make a video about that, maybe not. But music videos will come back soon, so keep your eyes peeled. And yeah, hope y'all find those as cool as I do.